This video is about trig functions on non-unit circles. And first, let's recall a few things that we already know. Over here in this unit circle that I have blank in the top left corner, I'd like to draw a central angle, which I will call theta for now. So it's an angle with the vertex at the origin, one side along the x-axis, and then another side I have extending out into quadrant 1. And I'm also going to draw arc T, which begins where our circle intersects the x-axis on the right side and then extends in a counterclockwise or positive direction. And I'm going to let it extend all the way to the side of our angle that's extending out into quadrant 1. All right, so as we know, this is what's called a central angle. Angle theta, that's labeled theta, and it's in standard position because of the fact that it's at the origin with one side along the x-axis and another side extending out through the circle in some way. Now we know much about this. I'm going to label this arc T, and let's recall a few formulas we now know about this. We know that T, the length of that arc, is equal to r, the radius, times theta. So the radius I could label up here as one of the sides of this angle. Now in the book you'll also recall that this is commonly written with S instead of T, so you might see S equals r theta. S is designated for arc length. We've also been using T for arc length, so either way is fine, but T might look a little more familiar right now. Now if r, our radius of the circle here, is equal to 1, then notice what happens to this formula. We get T equals r, which would be 1 times theta, or in other words, T equals theta. And this is to indicate that the arc length would be equal to the central angle. All right, so I'm talking about the measure of this arc, which is T, and the measure of this angle, which is theta. According to the fact that r could be 1, that would mean that those two items are the same measure. Now this would make sense. For instance, and let me just sketch another unit circle to start fresh with an example down here of a certain measure. Let's suppose that the radius of this circle is 1. Okay, well that would mean then that this is a unit circle. And let's say that I extend an arc up of length pi over 3, one of our special arcs. Okay, so we know where that would go. It would extend 1/3 of the top half of the circle, pi over 3. And we could say then that if I draw a central angle that intersects that terminal point and call that angle theta, then theta, if this arc is pi over 3, as I've mentioned, would also be equal to pi over 3. Now that's in terms of radians, or I could make it in terms of degrees if I would say 60 degrees. All right, now let's start fresh with a blank circle on the xy axes, which I have in the top left corner here. So I'll label our axes x-axis horizontally, y-axis vertically, and I'm not going to assume that this is a unit circle now. Remember, the unit circle has radius 1. We've been working with that basically exclusively so far, but now we're not going to assume that the radius of this circle is 1. I'm going to put a point on the circle in quadrant 1 and then extend the radius from the center, the origin, to that point. And I'm going to label that radius r for now because we're assuming that it's not 1 or that it doesn't have to be 1. Now if I end up making a right triangle out of this by extending a vertical line segment from the point where the radius intersects the circle in quadrant 1 straight down to the x-axis, and I'll mark it as a right angle, which of course means this is a right triangle. That triangle has an angle in the bottom left corner, which I'm going to call theta. Now, if you recall what we've been defining angles with, that is a central angle in standard position. It has one of its sides along the x-axis. That would be like the bottom side of this triangle, and then one side extending through quadrant 1 to a point on the circle. I'm going to label that point x, y, and recall again that if this were a unit circle, those coordinates would be the sine and cosine of our angle. Since this is not necessarily a unit circle now, let's discuss how else we could define sine or cosine since we don't automatically know the coordinates of this point. I'm going to put some other labels on this triangle, namely the bottom side of the triangle along the x-axis would have length x, right, according to this point, that would make sense, and then the vertical side, going from the x-axis up to the point, would have a length y, again consistent with the fact that the point is labeled x comma y. The way we're going to define our functions sine, cosine, and tangent, in this case where we don't know that the radius is 1, and therefore we can't just say that sine is automatically the y coordinate or cosine is automatically the x coordinate, is in this way. I'm going to take this triangle that we've drawn in quadrant 1 and actually just pull it out for a second so I can redraw it a little larger to see it more clearly, and then label some of its sides. So we have a right triangle, the one that we have already placed in the circle in quadrant 1 in our diagram, but I'm now redrawing it with the right angle in the bottom right corner, the hypotenuse across from that, and then the bottom side of this triangle we've already labeled x, and the vertical side, which is on the right side, I'm going to label y. And then the hypotenuse is going to be labeled r, since that would represent the radius of our circle when this triangle is drawn in the circle, as we've seen. And then I'm going to draw our central angle labeled theta in the bottom left corner, just as we had it in the diagram. All right, so there are some ways we're going to designate the sides of this triangle with names that we'll be reusing many times, and it's all related to where the angle is. So since theta is labeled in the bottom left corner, if I find the side that's across from where theta is, so look all the way across the triangle, it's the side that theta is not touching, that side we're going to call the opposite. I'll label it OPP for opposite, because it's opposite angle theta, or across from it. The R side length, which is labeled R, of course, if you recall where that came from, and that's across from the right angle, that's our hypotenuse. I'm going to label that HYP for hypotenuse. And then the other side that's not labeled yet, the bottom, where I have X labeled, since that is touching the angle, but it's not the hypotenuse and it's not the opposite, we're going to call that the adjacent side. So 3 labels for 3 sides of this triangle, and they all depend on where theta is. They're labeled opposite across from theta. Hypotenuse is always the hypotenuse. There's only one hypotenuse of a right triangle. And then the adjacent side is the other one that's left. That's also always touching the angle theta. Given these designations, the way we're going to define sine, cosine, and tangent is the following. The sine of theta is going to be automatically the ratio of opposite over hypotenuse. The cosine of theta is going to equal adjacent over hypotenuse, and the tangent of theta is going to equal opposite over adjacent. So these 3 verbally described ratios are how we are going to define sine, cosine, and tangent in this new way. And again, the whole point here is that these work whether this is a unit circle or not, and so we can automatically find sine and cosine of and tangent of this angle theta, this central angle. Now there's a nice acronym to help remember this. You may have heard it before. It's known as SOHCAHTOA. That's right, or said quickly, SOHCAHTOA. And the reason this is helpful is because these letters stand for the following. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So this little acronym is often a helpful way to remember these ratios, which we do need to remember. SOHCAHTOA. Beyond this, we're going to use the same definitions. Use the same definitions for other functions. And I'll give you an example of what I mean. Notice in this beautiful little SOHCAHTOA acronym, it defines sine, cosine, and tangent, but it does not define cotangent, secant, or cosecant. Well, we already know how those relate to these three basic functions, so we'll just reuse that. For example, if I wanted to find out what the cotangent of this angle theta is, I know that cotangent is really 1 over tangent. And we know that from defining cotangent previously. All right, but if I know that tangent is opposite over adjacent, then 1 over that would be 1 over opposite over adjacent. And using just a little flip of the fraction here with some algebra review, this is the same as the adjacent over opposite. So we can define cotangent as adjacent over opposite. But my recommendation is that you just remember or memorize these three basic ones, and from those three you can define cotangent, secant, cosecant, as we know already.